in the last class when we discussed about the solution of Dirac equation for free particle, so at some point we reached about the negative energy, and I thought probably it would be good to give a full overview picture of the negative energy because probably we're trying to understand the story how it is going on, and so for today's class there is two part as the time will permit. One of the part will be about the negative energy interpretation. Uh, and the second part will be the covariance form of the Dirac equation. So just to remind you what we discussed till now about the Dirac equation. So we try to get the form of the Dirac equation. We derive it in the last class where we mentioned whatever the wave function. The wave function we define, it is basically a bispinor field, or we call something Dirac spinor field. So today I'll try to give you some more deep interpretation of this spinor field. So the one thing is I use this term spinor several times. Let's try to just give a look what is the spinor is actually, what is the physical interpretation of a spinor. Spinor is basically a kind of mathematical representation which represent the spin half particle. And this is very important to know the spinor because the spinor which basically lead us to the Pauli exclusion principle. That's what I'm going to discuss today when we talk about the negative energy. And that help us to understand the stability of matter, and that is very important. So that's why the spinor at some point later, probably when we discuss about the fermionic field, we'll discuss in details about spinor. But just to give you the flavor, because this term I use several times. So spinor is basically a mathematical representation for spin half particle.
Okay. A quick question. So before the Dirac equation, the Pauli exclusion principle was not known. Is that correct?
The Pauli exclusion principle, well, I think it was going on parallel on that time because when
Okay.
when I today when we discussed that when Dirac was trying to interpret why the electron from the positive energy state cannot fall to the negative energy state, one of the main conclusion was come because of the Pauli exclusion principle. So
Okay.
probably
So
I
it's like a
exactly
further proof.
remember what time it was came up, but from this intuition what Dirac used to interpret the negative energy, the electron cannot fall to the negative energy state. So he used the concept of Pauli exclusion principle.
Yeah. See, it seems like I mean, the imagination comes first, imagination in the sense like prediction of like how the matter or energy will be present, and then we are running experiments or running mathematical calculations, and then which fall in place to those intuition. Like Pauli exclusion principle was the intuition that came first, and then the Dirac equation came later, and then they are able to see these negative energies. I know there is like a Pauli exclusion principle. Probably because of that, this is now happening. So now it matches, both match intuition and the
Mhm.
mathematical derivation
Mhm.
matches.
Mhm. Yeah, I'll check the exact time frame because I don't remember what time it was exactly developed the Pauli exclusion principle, but because of this intuition, I'm guessing it was probably going on the same time.
Okay.
So just to remind you, next like around 30 slides just to revise whatever we discussed to now. So I tried to make it like very concise slide so it will be easy to read also. So when we discuss the Klein-Gordon equation, what we discuss, we basically interested about the probability density function, not density function, probability density. And from the Klein-Gordon equation, we found that this probability density, it is proportional to the energy. And so the possibility of probability density would be negative if the energy, the given system, by default or by definition, if the sign of the energy is negative, then the possibility of probability density, it could be negative. So this is one of the conclusion we reached when we discuss about the Klein-Gordon equation. Okay, so the next thing, then we try to understand about the abandonment of Klein-Gordon equation. So historically, the problem of negative energy, which come from the come by default when you try to define, try to get it from Klein-Gordon equation. So the negative energy, there's two problem was right. One is by default the negative energy definition was there, and the second because this is the way how the Klein-Gordon equation was defined or yeah basically or postulated. And the second thing is also the negative probability density. So both of these two factor was basically abandon the Klein-Gordon equation. But later we already discussed that this is basically a kind of limitation of the Klein-Gordon equation. But when we further move to Dirac equation, this limitation also can be at some point merged together with Dirac equation and Klein-Gordon equation. So let's just to remind you what was the source of this Klein-Gordon equation problem. There was a two problem was there. One problem was the negative energy, and the problem of negative energy came because that's how the equation was defined or developed or the constraint. Because when we try to define or develop this Klein-Gordon equation, we start from here, the energy momentum relationship. So which is by default they have a possibility of negative energy. So this is one of the source of this negative energy which come by default into the Klein-Gordon equation. Then the second thing about the source of the probability density in Klein-Gordon equation, just to remind you about the Klein-Gordon equation, which is basically del square. I mean, you can write this as a de-alembertion operator plus m square, and the phi is the wave function. There is supposed to be equals to 0. And in the Klein-Gordon equation, there was del square del t, so the double derivative of the time, partial derivative of times. So this was from this equation, when we try to get the equation of continuity just by multiplying the complex conjugate of the given field, and if we do some mathematical calculation, we able to reach up to the equation of continuity. And from the equation of continuity, we can get this probability density. And if we consider the possible solution of the Klein-Gordon equation, if it is a planar solution, then if we just plug this wave function into the probability density, what we get from the Klein-Gordon equation is basically give us the possibility of 2n square with energy. So if our energy is negative, then the probability density also be negative. So this is the source of the problem, main problem of this Klein-Gordon equation. Not problem, but that is come by default.
Yeah, yeah.
Now, just to remind you about the way we try to deal with Dirac equation
Quick,
later.
sorry,
Yeah.
sorry. So quick question. So
Yep.
if, I mean, I think in the previous slide, a couple of slides ago, you mentioned about like Klein-Gordon equation was abandoned, but later reused.
Yep.
In what occasions Klein-Gordon equations was very helpful that Dirac could not solve, or Dirac was very complicated for that for that scenario? Is there any scenario
So,
like
so
that?
Klein-Gordon equation is basically a kind of simplification of the Dirac equation. Like if you remember, if you consider particle at rest, which is having the
Yeah,
rest
yeah.
mass energy, if we try to, or if you consider free particle if we try to get a solution of the Dirac equation, at some point, if we take some limitation, specific limitation, like if instead of considering like Dirac equation, it was by default for the spin up particle.
Hmm.
If instead of that, if we consider the spin zero particle, a bosonic particle, then the Dirac equation will be turned to the Klein-Gordon equation, which we're going to show today. At some point,
Okay, okay,
we'll discuss that.
okay.
So, what I mean that, yeah, so at some
So
point at that
Klein-Gordon
time,
is like a special form of Dirac equation, like a special variant of Dirac equation.
yes,
Basically, it's
it's kind
applied
of
for a
like,
non-spin
yeah,
particle.
it's like the kind of like one of the background story of Dirac equation.
Okay.
So this we also saw today. So this is about okay. The next thing what we discuss about how Dirac tried to postulate to tackle this problem. So the main approach was Dirac was trying to tackle this problem. He basically tried to go forward, a step forward. He said, okay, what we need our probability density is supposed to be positive. So he start from here. So he considered, okay, we want the probability density is supposed to be positive, greater than equals to 0. And what was his postulate? He said, okay, to get that, we need a equation. In that equation, the ddt or del partial derivative with respect to time is supposed to be linear in that equation. So that is the Dirac postulate. He postulated that. Right? Okay, we want to const because what is the problem? We see the probability density in Klein-Gordon equation was come to negative because of this time derivative.
Mm.
So what he postulated, okay, he know this is a source of the problem. So he said, okay, let's try to try to tackle the problem directly. We need the positive probability density, and as we know, it has happened because of this del square del dt square. Let's try to construct an equation where the del t to be linear.
Mm.
So to
Okay.
do that, and also there is one more thing what you also keep in mind, because other thing is the covariance of the form. So he want to construct an equation where the del t, the time derivative with the partial derivative with respect to time, that should be linear, one of the thing. And second thing, also he needs some equation where the if I just go back one step back about the Klein-Gordon equation, there was del square or grad square. So he want to construct an equation where the partial derivative with respect to space that also be linear. So these
Mm.
are two things he postulated, and then he postulated, okay, let's try to construct an equation in such a way that the time derivative, partial derivative with respect to time, it also be linear, and also with respect to space, it will be linear. So here I am using a little bit different notation compared to the previous class. Instead of considering DLT gamma, here I introduce another metric, which is alpha and beta. There is a relation between gamma and alpha beta. I'll come to the bit later. We will try to derive that. What is the relation between them? So here, basically, this beta and gamma, that they are kind of another representation of the gamma matrix.
Gotcha. So this seems like like just visually it looks like a Schrodinger wave equation.
It is
Like
actually
which,
it's a kind of solid, but not in non-relativistic case, but in the relativistic domain.
okay, because we are adding a why it's in relativistic domain.
So
Um,
so so
uh,
so just for you
we are
and
adding mass. Mass, that's why it's relativistic.
no, it is relativistic because if you look into the wave function, in the wave function, it's
Okay,
function of x and t, where
excellent.
the position and time they are treating in the same footing. So that basically give you the hint that this is an equation for relativistic equation of motions.
Gotcha, gotcha. And the m dot is
So this is
time
this
derivative.
this is not dot, sorry. This is some just typo.
Okay, okay, okay. So
So
beta
this is
m.
beta and m. M is the, you can for now you can consider the rest mass of the particle,
Hmm.
but it was not defined till now, but it's the rest, it will be the rest mass of the particle at some point. Okay, so so that is the postulate what Dirac was defined to get this. So the main idea, main story behind his mind, that we need a equation where the partial derivative with respect to time, that also be linear in the equation, because that's basically source of this negative probability. And also he need the equation with respect to uh, partial derivative with respect to space, that also linear because of the uh, Lorentz covariance. That what we're
Hmm.
going to discuss in today's class, because we will going to see later either the Dirac equation is Lorentz covariance or not. So but now the next question is, okay, we know what is a partial derivative with respect to time, we know what is a partial derivative space, but there are some new quantity also introduced by Dirac, which is alpha and beta.
Hmm.
So let's try to understand what will be the alpha and beta. So to find the condition of alpha and beta in the relativistic wave equation, so when I sometimes use this short notation RW, which corresponding to relativistic wave equation. What we need the first thing, we need a kind of like a proper definition of the energy and momentum relation.
Hmm.
So again, we start with let's start with the positive one, because at some point we don't need the negative energy, but because at this that point, because the possibility of negative energy was not known. So what we can do to get a kind of like a correct representation, let's start with the positive energy, which is basically, and this is also one of the kind of hint that we are in the relativistic domain, because we are using the energy momentum relationship due to the relativistic kinematics.
Hmm.
Okay, just to give you an, we'll discuss this thing a bit later, but also as I mentioned, when Dirac defined this equation or postulated this equation, back of his mind it was there about the Lorentz covariance. So the equation should be invariant or not invariant, should be covariant under Lorentz transformation. That means if you consider the phi is a solution, and if
Mhm.
we make a Lorentz transformation, the phi goes to phi prime, whatever the form of Dirac equation in phi frame and the phi prime frame, that should be same.
Okay, okay.
And this concept was already studied earlier also when we start, if we remember, when we studied this non-relativistic spin dynamics. In non-relativistic spin dynamics, there was a something called spin degree of freedom.
Mm.
So if you study this non-relativistic spin degree of freedom, there uh, it was already known because it was dominant in the non-relativistic spin mechanism, which basically derived by Pauli. Uh, so Dirac also used this concept of Pauli, where he used the concept of non-relativist spin dynamics. So just to give you the spin dynamics we're talking about. So in this slide, I'm talking about the non-relativistic one. So what is a sigma and B? Sigma is basically Pauli matrix, and B, let consider this for the magnetic field. I mean, it is spin orbit interaction. If you remember, if you
Mm.
consider spin orbit interaction, from the spin orbit interaction, we can, if we consider the quantum mechanical dynamics of spin orbit interaction, then we can get an eigenvalue equation due to the interaction of spin with the orbit or the magnetic field. Then whatever the chi, this is the chi corresponding to the spin field. Let's call wave function for not wave field at this point. Let's consider the wave function due to the spin half particle or this plus minus half particle. And whatever this energy, this is the eigenvalue, which is supposed to be a scalar quantity. When I'm talking about the scalar quantity, it's something is scalar under some transformation. So you can consider rotation. If you consider rotation is a one transformation, this energy should be scalar. It will not change the form of the form, or it will not make any kind of transformation. So it will be scalar under rotation. Similarly, whatever the sigma dot b in non-relativistic domain, that also a kind of a scalar quantity under rotation. And when I consider the spin in non-relativistic domain, whatever the wave function I define here with this notation chi, it's supposed to be a two-component spinner because
Okay,
it is spin up or spin down. So it will be a kind of two-component spinner. So this is the idea was already known that time. It was already on the market. Now, what Dirac tried to also use this concept later of this class, or if today or if not today or next class, we'll also discuss. I mean, whenever you consider the Dirac equation, there are many kind of, we use sometimes four vector, we use sometimes scalar, spinner. We'll try to understand later how those quantity and make a transformation under rotation or Lorentz transformation. So this part I'll discuss when I'll discuss. I'll take the note from there's a very famous book by Broken and Rail. So in that book I'll take the note from there, and they basically did that full derivation how the different field like four vectors, scalar, spinner, they make a transformation under different transformation, rotation or Lorentz transformation. Okay, so let me just go back one step backward. So what was the requirement? One of the requirement, we need a kind of a correct relation between energy and momentum.
yes.
Now, what Dirac demand once again? So this is a place. I think this answer of your question. I think one of the questions asked why I mentioned that at some point we'll use the Crane-Gordon equation also. So
Mm.
in the original approach, when Dirac tried to derive the equation, he said or he demand that whatever the wave function he defined. Let me go back to one step to one more. Yeah, this one. Whatever the wave function he defined in the relativistic space-time wave function phi, he demand that whatever be the solution it could be of a given solution, this should also satisfy the Klein-Gordon equation.
Okay. What are the solution that yeah, five we are coming up with because of
Yeah.
Dirac? So we had to solve that on the kg
Yeah.
also.
Yeah. So with some, obviously there will be some limitation, but this wave function should satisfy this Klein-Gordon equation. So it's not that Dirac was completely throw that
Ignorant.
Klein-Gordon equation. He used that concept. Okay, he know that okay there was some problem of this negative probability density, but he said okay, uh, in my formalism or in my postulate, whatever the equation I'm trying to derive, because that was the main idea or main motivation was coming from the Klein-Gordon equation. He said, okay, in my equation also, the wave function should satisfy the Klein-Gordon equation. So that was a kind of trick. Okay, we should again face the negative energy because the Klein-Gordon equation was defined in that fashion.
So, like I said, like the primary motivation for Dirac is basically so the probability density was like less than zero. He wants to solve that.
Yeah.
I think to me that seems like the primary motivation
Yeah,
because
that was the main important
any
because
equation starts
we know
from EG.
basically mathematically we know probability never can be negative. It will be
Exactly,
it will be from 0 to 1. Usually it from 0 to 1 in mathematically. So the probability
exactly,
density it cannot be negative.
exactly. But he knows that the kg always starts from relativistic ENP relationship, right? E square is equal to
Yes.
P square M
Yes.
square. Even kg starts like that.
Yeah.
So yeah, the probability density is the primary motivation for him to solve. And then
Okay.
he liked the linearity of I mean he wants something linear, like dou
hmm
by linear in the first derivative of time and then linear in first derivative of the position.
Space. Yeah.
Yeah.
So this is actually the main savior for him. Uh, okay. So what do we reach till now? So we get this equation. Now we need what we are tried. We are trying to get the kind of what is the relation, what is the condition of alpha and beta because that's kind of unknown. So he was trying to get a kind of what you call the Dirac matrix. So we are trying to get a condition or relation of this Dirac matrix. So this is a Dirac equation what we already discussed. Then now you can do one. You can take a complex conjugate and you can just taking uh, do the matrix multiplication or in a more general way you can just be squaring the both
Mm.
side on the operator terms. If I do that, last time we also did this one, but that is we did in terms of gamma matrix. So I'm just trying to give you another way also is available. So if we just multiply one by one, so I just take this one, make a square in both side. So just multiply this. So if we just do this mathematical one, you can just I write it in a compact form in notation of summation
Mhm.
notation. So I have some notation, some first term with this, which is partial derivative with respect to space. This is one of the term I have, and this term and this term, these two terms were not there in Klein-Gordon equation. So
Mm.
if I just remind you the Klein-Gordon equation, because that what Dirac demand that his equation should
Those
satisfy also the Klein-Gordon equation.
those कैसे hypotheticals
Yeah, so
करेंगे?
in Klein-Gordon equation, this term, this alpha square minus alpha square, this term also not there in Klein-Gordon equation. This beta term also was not there in Klein-Gordon equation. So this alpha square that's supposed to be equals to 1. This beta square equals to, sorry, this alpha square is supposed to -1 because there's a minus sign here.
Mm.
This beta square is supposed to be identity. If I talk in terms of matrix, it's supposed to be identity matrix. Alpha square will be identity minus of identity matrix.
Mm.
And these two terms should be vanish
Vanish, yeah.
because this kind of term was not there in Klein-Gordon equation.
Yeah.
So to do that, okay, so just to remind you that what we need, if we just put this term equals to 1, this term equals to 1, this two term 0, then we will be reached at some point up to like similar to the Kerr-Gordon equation. Okay, so whatever the condition we get, the condition is that this product term or these two are the product we get from sorry we get from this is one of this matrix multiplication alpha I alpha j plus alpha j alpha I. This term equals to 0. This term also be 0. This will be 1, and this alpha square, that also be 1. So this will be the kind of required relation which was unknown before we reach up to this point. What Dirac was trying to get the equation which is similar to the Kerr-Gordon equation, and this kind of relation which was already known in terms of Pauli matrix, Pauli spin matrix.
Mm.
So
Normally, this will not come right. Like alpha I beta plus beta alpha I. I mean, normally this should be like 2 alpha I beta normally. But if something like this, this seems like this is not commutative.
so this is the relation we call anti-commutation relation.
Exactly.
So this
So
anti-commutation relation, it was already known that the spin matrix, the sigma matrix also had this anti-commutation relation. Okay.
so the only place that can have anti-commutation is like, I mean, one place I was like looking at some of the YouTube videos.
Mhm.
So the only way we can get this anti-commutative property is like by doing cross multiplication. So sorry, cross product. Only in cross
Yes.
product the negative so that means like this alpha and I should be a matrix. It cannot be like a scalar value.
No, I mean, even if you're not going into this way, still if you just look into Dirac equation, then also you can understand this is supposed to be a metric, because whatever the Dirac equation was defined till now, so this is a kind of derivative with respect to space, the three component derivative. So if we try to convert it into some other representation, the matrix will be only one possibility.
Yeah,
Like you
yeah,
said, if you do this matrix multiplication, uh, like kind of cross product, you get this kind of similar relation.
yeah, anti-commutative relation. Yeah.
Okay, so the next question is what, then you try to understand what is a natural choice for alpha and beta. So in non-relativistic spin particle dynamics, it was all, if you just keep into that in mind, that alpha and beta, that's supposed to be metric, as you just discussed. And what kind of matrix it will be? It will be kind of like column vector, because
Um,
that's give us the possible choice of the spinor field phi. So therefore, it was expected that Dirac equation represent the particle with spin half. That was come by definition, that whatever the Dirac equation was defined, that was similar to the spin half particle in non-relativistic domain. So
okay.
when talking about the Dirac equation, we basically represent the Dirac equation for spin half particle, or the spin, not spin half, but spin half with the odd integer of the spin. That means for all bosonic particle, the Dirac equation should work.
Mm.
Now the question is, okay, we know that alpha and beta, those are supposed to be metric because of this spin mechanism we not known from non-relativistic spin mechanism. Now we also try to understand what will be the dimension of this alpha and beta. So to define the dimension of alpha and beta, if we try to just keep in mind how we define alpha. So this alpha was this is how the Dirac postulate. It is defined in terms of Pauli 2 by 2 Pauli spin matrix. So this is basically a 2 by 2 null matrix, like 0 0 0 0. This is 2 by 2 Pauli matrix. It could be like sigma 1, sigma 2, sigma 3.
Mhm.
And so this alpha, this supposed to be kind of like a 4 by 4 matrix.
Yeah.
Similarly, what are the beta? This beta is basically defined in terms of identity 0 0 and minus identity. Okay, so now also we can do little bit more mathematics. This is the kind of I added some of the homeworks in this note, where I'll ask you to just to do this kind of mathematical calculation to show this two relation about if I consider two matrix alpha and beta. If I take
Mhm.
the anti-conversion relation, I mean this alpha I beta plus beta alpha I, if we just do the matrix multiplication, it will be always zero.
Okay. Okay.
And for alpha and beta, if I take anti-conversion with alpha with two different index, I and j, this will be like 2 times this conical delta matrix. And
Yeah.
this beta
Conical
square
del ij will be like 1 for I is equal to j, will be 0 for I not equal to j.
not equal to j. Yeah. And this beta square, this is a identity matrix. This is what we get by definition from the Dirac equation. Also, later when we discuss about the covariance of Dirac equation, that time we will need this information. So I think to just keep it in mind. Now this, as it is a matrix, alpha, we already know this alpha and beta are a matrix, and this matrix can also do kind of transformation. So this matrix, but not all possible transformation are allowed in terms of spin matrix. So only possibility of the transformation is supposed to be, we can consider any kind of transformation, but the transformation is supposed to be unitary. So whatever, if I consider alpha and beta, which are the 4 by 4 matrix, if I want to do a transformation of those alpha and beta, I need a unitary matrix which is supposed to be 4 by 4. Why we need this unitary matrix? Because we want a kind of transformation, but before and after the transformation, the anti-commutation relation between
The
alpha
alpha and
beta
beta.
or alpha and I mean this anti-commutation relation, it should be preserved because that is come by definition from Dirac equation. So we are not allowed any kind of transformation. We will allow only those transformation which help us to preserve this anti-commutation relationship. And that is only possible if we make a transformation which is a unitary transformation. And mathematically, when we represent unitary transformation, even in quantum mechanics also, if you remember, we use this kind of transformation. You can take a matrix, make a transform rotation, and again, if you make inverse of that, you should get back to the original matrix.
Mhm.
That only make ensure the anti-commutation relation between alpha and beta or in between them, it should be preserved. So this will again we come back later when we talk about the covariance form of Dirac equation.
On the previous slide. So I'm just thinking like, so if I make a different choice of alpha beta, will I get like a different type of particle? I mean, I'm just thinking like imagining like
Mm-hmm.
into, I mean thinking like for example, one choice of alpha and beta will give me like a fermions. Another choice of alpha and beta might give like a, I'm just nonsense here. Another choice of alpha and beta will be giving me gluons. Another choice of alpha beta will be giving me baryons. Is there something like that? I mean, can we imagine like?
No, I mean, whatever the dynamics we discussed in now, or whatever the kind of till now we did not talk anything about some generating of new particles or something. What we try to understand dynamics of the particle.
Okay.
So by definition, when we try to define the Dirac equation, so the choice of the given matrix alpha and beta, we try to what we want. We know the what kind of relation of alpha beta we already understood, and then we try to understand what could be possible choice of alpha and beta, and then the concept of non-relativistic spin mechanism, it was already there, and we know the spinner or the spin matrix, the Pauli spin matrix, those also had a similar kind of dynamics or similar kind of characteristics or similar kind of properties. So, so to understand, so we just try to make a one-to-one analogy between them, and we can see there is a possible analogy with the spin half particle or spin half with odd integer particle. Those are the kind of similar dynamics or similar kind of property or characteristics. So we just adopt the concept of this spin half particle with or spin half of odd integer particle concept to interpret the possible solution of alpha and beta matrix representation. So here, I mean, this spin can be like spin half, spin 3 by 2, spin 5 by 2, spin 7 by 2, whatever the odd integer you can choose. And all of them, so those you can make kind of group of particle, and all of the kind of dynamics or mathematical properties for those should be identical.
Mm.
Okay. So to answer your question, is that till now we are not. If you try to think a different choice of alpha and beta, we obviously we can think, but those should be fulfill this if there are some different choice where alpha and beta could be different, but those relation this anti-conversion relation should be there. if it is possible, then what will be the answer of that? Then okay, yeah, if we find a defined choice, those particle dynamics we can also study using Dirac equation.
Okay, okay. Yeah, yeah, sure,
So,
sure.
that means that what that means will mean that uh, it's not that we are generating a new particle, but if there are some particles which have defined combination of spinor representation or matrix representation, that we can replicate exactly same like what alpha and beta can do to understand a Dirac equation representation. Those choice of alpha and beta for that particular particle, with the choice of this alpha and beta, we can study the dynamics of that particle using Dirac equation.
Gotcha. I mean, we can think it like, I mean, just for my easy
Yeah,
understanding,
yeah.
when you always think about dynamics, the dynamics is nothing but we want to know the position, velocity, momentum,
But
basically.
now we are in the relativistic domain. So when I talk about dynamics, that means how the space time is changed.
Yeah, how the space
That
time
means
is
if we
changing,
now we are talking in terms of field, so we trying to understand dynamics means we try to understand how the field is propagate.
how the
That's
field is
that's
moving. Yeah,
that's
correct.
what we are interested about.
Exactly. So, like, just to draw a parallel, right? I mean, like in Newtonian mechanics, the dynamics of the particle is defined by F is equal to ma.
Yes, yes.
Yeah.
So in
And of
Newtonian
course,
mechanics, suppose we use this kind of term very often, that dynamical variable, like
yeah,
position. So if I
yeah,
write position as a function of time, that means how the position is changed with time. If I when our time change,
the
either the
position.
position is changed. So if so that when I talk about dynamics in Newtonian mechanics, that is how the position or any kind of variable, what we are interested about, how it is changed with time.
Exactly,
Yeah.
exactly. So in that, like the M plays a role of like it is not a new particle, but how the dynamics or the position of the particle changes when the M changes in Newtonian. In the similar way, like this alpha beta plays the similar role. I'm not saying M alpha beta is equal to M. It is just
Mhm.
a constant. It
Yeah,
just
yeah.
affect how the
Mhm.
wave function is changing.
Yes, yes. So if suppose tomorrow I come up with some different particle, suppose, then and I think till like from the beginning of physics, how it is started. If you have something new, we always try to understand how it's changed with time or how the dynamics happen. So
Yeah.
or how, I mean, if I talk in terms of four-dimensional space, how the space time is changed. So
Mm.
then the first thing, if we have some mathematical representation that we can try here to understand either Dirac equation is well enough or not to understand the dynamics of the given system. Basically. Okay. So this is one part of the lecture what we already discussed uh, one class further, or I think two. Then in the last class we discussed about the possible solution of Dirac equation.
Mhm.
So to do that, we start with, so okay, today what we discuss new, nothing new, but a kind of defined way. Like in last time, I used kind of like gamma matrix. I'll show you what is the relation between gamma matrix and alpha matrix. But this is also one of the representations sometimes used in different notation. So I just like you to just let you know that this is also one of the possibility you can think on that way instead considering alpha and beta. Okay. Now, also this thing already discussed about the free particle solution. To do that, we try to understand what is this spinor phi. So this
Mhm.
spinor, this is basically a kind of four-component column vector, which we define further as a Dirac spinor. Now, this is again from the non-relativistic quantum mechanics. So what I'm trying to doing here. Now we are in the relativistic quantum mechanics domain, but time to time I'm trying to give you the idea of non-relativistic quantum mechanics because this is kind of going parallel. I mean, this is a thing what is known. So when something new come up, they're trying to use the concept what is already known. So this
Mhm.
non-relativistic quantum mechanics was already known for the spin-up particle, spin-up spinner, spin-up spinner. So just to use an analogy with this non-relativistic quantum mechanics for spin-half particle, the possible solution of the wave function in non-relativistic quantum mechanics. It has some two-component spinor, which we already discussed. This is a two-component spinor, and some plane wave or representation, which basically give you how it is evolved in the space-time.
Mm.
But in case of this non-relativistic case, this chi, it was 2 by 2 spinor. But now, in case of Dirac equation, we need something which I define here with omega. This omega is basically not 2 by 2, but it's 4 by 4, or
Mhm.
not, yeah, or we call it, now it was 2 by 2. It was like a spinor, two-component spinor. Now here, what we need something called four-component spinor, and we call it now like a bispinor. So to do that, we
Okay.
define this. This is already discussed last class, but we can define this omega as a phi and chi. So this is the notation I like to use. And
Mm.
along with that, they are supposed to be a kind of plane wave solution or plane wave representation.
You can go to slide 23, the previous slide. So, non-realistic economic solutions of spinor halves by analogy with the female, right? The general. So, in non-relativistic case, we are writing the solution of the equation as a two-component spinor.
So like it's like if you consider the quantum normal quantum like Schrodinger equation,
Yeah.
and if you try to solve the dynamics of spin half particle in non-relativistic quantum mechanics, it is already well developed. If you just give it, I guess it is chapter 4 or 5 where they discuss about the spin orbit interaction. If you look into that part, in Griffith book also, the wave function for non-relativistic spinor, it was defined the spinor part, which is multiplied with the plane wave part. So this is just, I'm going to show you the analogy how the same concept we use in Dirac equation also. You have the spinor part, and this is plane wave.
The Feynman equation. So the spinor part, yeah, spinor part is two components and here is four components. Okay.
Okay. So, and also, if you just remember in the last class, we also try to get this relation. We derive this basically mathematically derive this relation uh, in between in terms of matrix representation. So here, this is basically a omega, and this is some matrix. I mean, I think I saw in other way around. I saw it was kind of like a eigenvalue equation. I have an
Okay.
operator, basically matrix, operating on the spinor. I get some energy eigenvalue and the spinor back. This is
Mm.
already we discussed in the last class. And then from there, we try to derive a kind of coupled equation. Just if I just do the matrix multiplication, we can get this two coupled equation, where one is with phi, where E minus M is the energy state, and other is chi with E plus M, the energy state.
Mm.
And then also we tried to we did some more mathematical calculation. Then we find out what is the possible spinor state or possible one of the solution, and we define the solution one with this phi. So there we define two. I think total four solution was there. One for the spin half positive energy solution, spin up negative energy solution, and spin down positive energy, spin up positive energy solutions. Okay, so now again, just go back once, ask the same question once again. What is the relation? Because this is one thing we are interested about the energy momentum relationship. So do that, if we just go back to this, if we just again start from here, just do something replacement here and there, then we can find out this equation, just replacing, just trying to solve this two coupled equation. If we try to solve this one, then we can find some relation that this E minus M, what I get from here, this E minus M and E plus M, and then which is equal to P square psi. What that mean? That means this is a kind of, if it is true for all possible solution of phi, that means E minus m times E plus m, that equals to P square. So what I can get from here, E square equals to P square plus m square. So what is the possible solution of energy we can get from the Dirac equation free particle solution? Again, we can get two possibility. One is plus and minus. So the possibility of this negative energy is still active or still valid when we try to solve the single particle or free particle solution concerning Dirac equation. But what we got till now from the Dirac equation, I mean, if you remember, we discussed this thing. If we now, do I have it here? Yeah. So what? So the possibility of negative energy solution is still valid, is still active. But what we get a kind of one of the important question what we start that the probability density, which was negative in Kerr-Gödel equation. If we do some mathematical calculation, then what we can found that probability density in Dirac equation, which is nothing but the complex conjugate or the Hermitian of the wave function with the product of the wave function. And this quantity never can be, what that means, it means if I consider this matrix representation, the psi I can define like psi 1 star, psi 2 star, psi 3, psi 4. This is the complex conjugate part and the psi 1, psi 2. And if I do the matrix multiplication, what I can get nothing but that. It was like psi 1 star, I can just write it somehow.
Psi 1 star, psi 1,
Yeah,
psi
it will
2
be
star.
like psi 1 star, psi 1 plus psi 2 star, psi 2 plus psi 3 star, psi 3. And this is nothing but your modulus of psi square, right? So what we got from the current probability density, what we can get from the Dirac equation, it will be always positive. There is no chance that the probability density will be negative anymore. So one of the problem was solved. This was very important one because this is the place where we started with Dirac equation or the Killing-Gordon equation, that Dirac want that probability density should be positive. And this has happened how he generalized the equation. He started with, instead of wanted to construct an equation where the partial derivative with respect to time will be linear, because that was the main source of the negative probability density. And also by default, he defined the linear of the space derivative because that was give you the Lorentz covariant form of the equation. So one of the problem was solved. It is positive now, but the possibility of negative energy is still there. And also this thing also we needed later, which is like also if you just do the mathematical I have this note what I gave you already. If you do this mathematical calculation, you can also calculate what is the probability current.
Correct.
And this probability current, this is now we needed this probability current concept because now we are trying to we will be later when we go about different kind of scattering, the what is the length or the coupling, when we have two kind of the point where the scattering happen, if I try to understand the strength of the coupling, that will be we'll discuss later in terms of the probability current density, and that also we can get from the TI equation. For so now what we reached in now, we are considering spin up particle or spin up odd integer particle, any fermions. So for all fermions, whatever the interaction will be there, that for that interaction, the probability current density, it will be positive with what we get by default from Dirac equation. And also probability current, the vector component, that will be psi dagger psi, the alpha. The alpha is a matrix what is there in the Dirac equation, and alpha x. Okay. So to summarize this concept of Klein-Gordon equation and the equation. So from the Klein-Gordon equation, we had
We get
negative
negative
probability,
probabilities and negative
negative
energy.
energy. From the equation, we get the positive probability, but still the
And
possibility to get the negative energy is still valid.
mm,
Okay, now the question is, this is the place where it was the main part of the today's, and one of the first part of the student video about the negative energy. So the concept of negative energy is still valid. So now Dirac first tried to interpret this negative energy. He said, okay, see, whatever I able to do, I did. So now what we can do, so the possibility of negative energy is not something just mathematical one. It's not just come from mathematical concept. So he tried to interpret that, considering what we call nowadays like Dirac Sea. So at least for this free particle if I consider free particle Dirac electrons, the possibility of positive energy and negative energy that is symmetric with respect to the energy zero. So in this diagram, whatever this level, this is corresponding to energy zero. So the possibility of positive energy level and negative energy level that are symmetric with respect to the zeroth energy state. So this is I defined all for the and also it is continuous. It's not, I mean, at this till now you consider the continuum state of energy positive and continuous state of energy negative, and it's extend up to infinity. Okay.
Okay.
Now what Dirac? I think this is a question what you asked in the last class also.
Mhm.
Uh, why the possibility of electron? I mean, let's consider this electron, the red one, the red dot I'm drawing here. So this is the one of the electron in the positive energy state. Now this electron cannot easily fall to down state negative energy. The question of what, and this was a question also what Dirac was thinking, and then he said, okay, this is a thing what we not observed in nature,
Mm.
right?
Yes.
So then what he said, okay, we need a theory which can prevent the fall of this positive energy electron to the negative energy state. So to do that, he make a postulate or kind of what is the postulate? So in order to prevent the positive energy electron make a transition to a negative energy, we have postulated that if I consider the normal empty state, I mean the like which is basically called sometimes vacuum state, there will be no positive energy electron present. So if I consider a vacuum state, in the vacuum state there will be no positive energy electron,
Positive, the vacuum state, no positive energy electron, negative energy electron.
positive energy electron.
Okay.
This is his postulate.
Okay.
Let's try to understand why what is the consequence of this postulate. So
Okay.
whenever you consider the vacuum state,
Mm-hmm.
let me go back to one step further. So Dirac postulated that, so whenever you consider something called normal empty state, which is now we call this a vacuum state.
Mm-hmm.
So when I'm talking about the vacuum, it's like infinite extent state which having like infinite charge and energy. And
Yeah.
and this vacuum state it is filled with all negative electrons. So there is no possibility of positive electrons. This is what I guess I said the same thing in the previous slide. I said the no positive energy electron present in the vacuum state. So whenever we consider vacuum state, according to Dirac postulate,
Okay, okay.
it is
So what is he
consist
saying is
of,
what is he saying is that in a vacuum state, there is no positive energy electrons, so you are allowed to fill positive energy electrons.
yes, exactly. So this is
Like,
how I basically trying to quote his word. That's why I'm
yeah.
just quoted here. So when he defined the vacuum state, which is basically normal empty state in our simple word or simple language, because the vacuum word is very scientific word. So whenever we define something called vacuum state, which is basically the possibility of infinite charge and energy,
Mm.
and the state will be completely filled with negative energy.
Mm. But the concept of negative energy is like,
I mean, negative energy
can we
electron.
create negative energy? Like we can create positive energy.
Sorry, one
We
second.
can convert positive energy. Like we know how to convert positive energy, like electrons from one level to another level. But we don't know how to create negative energy, right?
yeah, that's what that's the reason why he trying to postulate on that way. He said, okay, what is the main idea here? He trying to make a postulation or this postulate because from the nature, we know from the nature observation that there is no possibility that electron can jump to higher energy state to lower energy state until it is spontaneous at some point. So why it is happened? So he trying to postulate that okay, there's a possibility to define a kind of state which is infinite state, and the state is completely filled with negative energy.
Mm.
Right. So
I got that
now,
part.
now
I
what
got
is it? Now, sorry, I just bifurcated by your question. What is the question you asked? Can you repeat the question once again?
the question is like we can create positive energy.
We can create positive energy, okay, but question is still now we don't know how, because this is because
No,
okay,
positive
at
energy
this
we know.
at this point we know at now we know how to create negative positive energy, or but at that point, I mean, based on the story we are going on, the storyline, till now we
Okay.
don't know how to create this positive energy, right?
Right. But even now it's okay. But even now we don't know how to create negative energy.
I mean, uh, again, it is kind of like a what is called positive, how you consider it. If you consider positive energy, negative energy, I can consider negative energy antiparticle. So if you consider the antiparticle concept, then it's
Mhm.
possible, right?
Okay, 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 okay.
I mean,
So,
if you just think in
sorry, sir.
the
Sorry, the
other
reason why I'm saying this is like just funny
so if
thing.
you consider particle, the
Mhm.
particle negative energy is difficult to produce because again this is again because the state is completely filled with negative energy, right?
Right. Right, right. I got you. Like, I'll come to that question of like, I'm just trying to like imagine. I mean, the funny thing, the funny thing is that you heard about you know Star Wars, Star Trek.
Yeah.
Star Trek. I mean, the engines that they use is warp drive, and the
Mm-hmm.
warp drive can like travel like faster than the speed of light.
Mm-hmm.
And there is the branch of, I would not say science or pseudoscience, whatever we might want to call it, but there are like prominent professors,
Yeah, I
even
think
in
J.C. Sudarshan, he posted one particle called trachyon, which can move
Harvard.
the faster than speed of light.
Yeah, yeah. So that is one concept. Other concept is like they're trying to create this warp drive. The warp drive that was like science fiction done in Star Trek. They tried to create this warp drive, and then they came up with the equation. And in that equation, what they said is like, okay, we need to have negative energy. If you have negative energy, then we will be able to create warp drive. But there is no negative energy. So that is why, that is how that warp drive concept goes. I
Mm-hmm.
mean, I'll share you one. I mean, I recently met, I mean, at least through LinkedIn, recently met a professor. It's called Chance Glenn. He wrote a paper on like warp drive, where he said like, okay, we need negative energy for creating that faster than the speed of light. I'll send you that paper. But
Mm-hmm.
there they're asking like we need to create negative energy. But even with the Dirac, right? Yeah, the equation predicts a negative energy, and equation says that this negative energy state is like completely filled. That's why like electrons will not jump.
Mm-hmm.
Uh, Electrons will not jump to the like from positive to negative. So it will not jump because it's completely filled. So
Mm-hmm.
that is how we are thinking. And the other way to think is like okay, the negative energy we can think it like antimatter.
Exactly.
Antimatter is of a negative energy.
Mm-hmm. Yeah,
So that is the way we
yeah,
think.
yeah. So if you want a negative energy particle, that will be by definition to be antiparticle.
Hmm. Okay, okay.
Yeah. So just to complete this story, so by the postulate of Dirac, so when you consider the vacuum state or the empty state, it is filled with negative energy. So if one electron want to fall into this vacuum state, but it is already filled, so the
Oh,
Pauli's equivalent principle was there. It doesn't allow to in one state. It can allow only two possible electron. One is spin up and spin down. Electron or position particle, whatever you consider. so it does not allow to accommodate one more electron in the so that's why the vacuum state, I mean, until and unless there are really some empty space, I mean, some particle is moved from negative energy to higher state, positive energy, there is some empty state, then one electron can fall. But if I consider a vacuum state, then it is not possible.
Mm. Okay.
Okay, so just to give like more precise storyline. So when I consider the vacuum state, it is basically defined as an infinite state of infinite negative energy and charge. So so that's how I define. I consider a state which is filled with negative energy.
Can you go to the next slide,
Yeah.
37? So it says like from observation represents finite fluctuation in energy and charge with respect to vacuum.
Mhm.
Um, uh, Maybe, okay. I saw in some of the YouTube videos when they discuss about the field theory, quantum field theory. So what they say is like the field is not constant. The field is always like there is some kind of fluctuation. Like the field always like there is some kind of fluctuation, not perturbation, some small fluctuation.
Mhm.
And only sufficient amount of perturbation on the field will create the particle. So now this line from observation represents finite fluctuation. So is that what we refer to as like the like in a vacuum state, the field is not constant, it is fluctuating. Is this what we are talking about the negative energy?
Uh, so uh, so that these two are not really one-to-one interconnection.
Mhm.
The thing what I want to interpret here in this slide. So I define, so this is a definition of vacuum state. I said when I define the vacuum state, I said it is a state of infinite negative energy and charge state.
Yeah.
But if there are some, like as I said, when one particle is created, or so there is some perturbation, there is some, but as you know, there is some fluctuation, and the fluctuation generates some particle. But till now, it is this is basically the further theory of normalization quantum field theory or something. This is another storyline where though we observe only in a finite fluctuation in the system, but that finite fluctuation is not, because what but from the theoretical point of view we can assume it as an infinite source of energy, but to achieve in the state we need to renormalize the state or revise the system, which will not allow us to do these infinite fluctuations, because
Okay.
that what we not observe. I mean, theory should be defined in such a way that it's supposed to be kind of at some point matched to what we observed in the nature.
Okay. Okay.
So probably I missed your question. So your question was.
And my question was like, I mean, in a vacuum state, there is minor small fluctuations on the field.
But
The
just to
fluctuation
clarify
are
here, Tina, we are not talking about field yet.
okay, okay,
Okay. So when we come to the field, then the scenario will be a bit of different.
okay, okay, from observation.
But though
Like,
at this point we are considering this phi is a spinor field, but we don't represent it as a field yet. So when we come to the spinor field representation, then we can see how this infinite fluctuation in the vacuum also treated there.
okay, okay,
So just for a time being, and just pause this part, because if I consider the field here, and then we need to make a lot of assumption before to go this infinite fluctuation, how to handle it.
okay, okay, okay. One silly
Yeah,
question maybe,
yeah.
like in the negative energy, right? What is
Mhm.
the ground state of a negative energy? Like in a
It's
positive
go up
energy,
to
the ground
infinity by
state is zero.
definition of Dirac. It could be the infinite state, right? So when you
So
consider,
negative infinite is the ground state, right?
yes, that's how it's defined. But now the question is how we define infinity.
Now I was thinking like, should it be like negative zero? No, like
I mean,
zero
negative
to
zero
zero.
is not something. I mean, concept of infinity is so funny. I mean, it's defined what frame of reference you are considering, right? That's you give you the definition of infinity. But there is at this, I mean, here when you consider infinite state, it's very difficult to define what a ground state, because it is like an infinite extent state. So that's why it's called the Dirac Sea. It's not possible to define what is the end point.
Okay.
And so this is so there's now at this point there's till now the concept of Dirac and Feynman was going parallel. Feynman was agreed up to this point, but here what also Dirac considering here, he considered if one negative energy electron is, I mean, if suppose one electron at some point jump, if I just trying to draw here,
Mhm.
so as it is, as you know, it is completely filled. If one electron is jumped from here to here,
Mhm.
because of some additional presence of energy from like you know from the pair production, he said okay, there is an absence of negative energy electron here, and
Yeah.
this absence of negative energy electron he defined as a hole. This is called Dirac postulate on hole theory, which was not Feynman did not like it very much. I mean, he said this is something unnecessary to make the system bit more complicated.
Mm.
So if we consider the concept of hole, that means now you started with a single particle theory. So you are what you are how you started. You try to understand the dynamics of a free electron. You try to solve that problem, and now you started from one single particle. Now you come to the multi-particle system. So the system, the physics will become more complicated.
Mm.
That's why Feynman doesn't like it. So though, but what Dirac was postulate, they postulate the absence of electron in the Dirac sea, in the infinite sea, uh, which is basically he defined it as a whole. That means negative energy will be positive energy, and the negative charge will be positive charge. And just to complete the story, it was all I think discovered in 1932. The positron, which is I think the first antiparticle, was discovered in 1932. No, not I think it was. I think it's discovered 90 or it was Nobel Prize was given 930 out of two. I forgot which one, but I guess yeah, it was discovered in 1932, and later I think Nobel Prize was given to Carl Anderson for the discovery of antiparticle, and that was basically a verification of Dirac all hard work to start from Klein-Gordon negative probability density to positive probability density with all this mathematical juggling, and then he introduced the concept of antiparticle, which is the absence of positive negative energy, absence of negative energy electrons. That what he will later define as an antiparticle.
Hold on. So absence of negative energy particle is an antiparticle. Can you go to previous slide 39?
Absence of negative energy electron. Yeah, I mean, yeah, so absence of negative energy electron that's equal to presence of positive energy positron.
Oh, a negative energy electron. So
Electron, not yeah. I mean,
negative
absence
charge
of negative
electron,
energy
negative
particle,
energy.
that is presence of positive energy antiparticle, right? If I just try to draw it once again here in the previous
Yeah,
diagram,
yeah, yeah. So okay. Negative energy electron.
yeah. So in this here, I have negative energy electron. If this is going jump to here, so there will be absence of negative energy electron. That is that is how we define as a positron.
Mm.
Wait, now I am also confused. So absence of negative energy electron, that will be like okay. So if I consider antiparticle, so the antiparticle itself like negative energy.
Exactly.
So I mean, wait a moment. So if this electron is if this negative energy electron is moved to the state, so I have like electron here, and also I have one. Okay, so this one is negative energy electron. Sorry. So absence of
Yeah,
negative
I
negative
think I get
energy
it. I think when
electron.
it's like negative energy is moving from this yellow line to green line, right? Negative
Yes.
energy electron. So when a negative energy electron is moving from there to there, then that becomes like a positron. That'll be seen like a positron.
Yes. So yeah. Okay. Now I get it. Yeah. So So we need to define how and when I consider positron, it itself like a negative energy electron.
Yeah.
I mean, if I just write it, energy of electron equals to minus energy of positron. This is by definition. And
Hmm.
already it has another negative energy because it is in this state, whatever the state I define here. So there will be one more minus sign. So it will make like positive energy positron. So when I define the positron, if I compare with electron, so it is already negative energy by
Mm.
definition, and
Yeah.
it's belong to a negative energy state. So that's why I think that's why you define in this absence of negative energy electron, it is present of positive energy positron.
Mm.
So this is like two minus sign will be there. So
Yeah.
that to be positive. Okay, so but the story, important story here, one more thing is that what Dirac started, what we start from the single particle theory. We try to
Mm.
understand the dynamics of a single electron. But if I go with the Dirac postulate, I'll be done with the multi-particle theory. So instead of electron in the final state, now I have electron and positron, two particle. If I try to distinguish them on that way. And I mean, this is just kind of showing you how the two particle concept come up. Like when if there is a presence of at this external photon, you can get an electron and one hole. So in the final state, you have two particles. So electron and positron.
Yeah.
So that's the thing. What Feynman did not like. This is one thing. And the second thing, but the question is still valid. What question? The question was that what about the negative energy in Klein-Gordon equation?
Mm.
Because that was not solved. But one of the problem was solved the negative probability density.
Mm.
So what was our main postulate here, or the idea was when Dirac tried to interpret this concept of the spin half particle, he was successfully did it. He get the probability density function. But he said, oh, now Dirac also tried to get the same thing for spin zero particle.
Mm.
And then he was failed to get the energy for spin zero particle, the positive energy for spin zero particle. So the question is, whenever you consider the bosonic particle, as you know, the bosonic are not, they are not fall into the Pauli exclusion principle also.
Yeah. Only
Only
fermions.
the fermions for the Pauli exclusion principle. So the Dirac equation was the Dirac formula, the Dirac interpretation was not successful when you consider the spin zero particle. So
Mm.
it's oil enough for the spin up particle. So that's why that's why we need to make a kind of barrier or kind of like a thin line what Dirac and Kerr was doing. So these two are kind of, though at some point they merged together, but they had like a very thin line between them. One was Dirac was mostly dealing with the spin half particle. That is how it's come with his own formalism.
Okay.
Okay, so I have still few more slides for this slide, then I'll take a break. So just to complete the story, what Feynman did in his theory, he considered the whole theory, which is basically give you additional constraint to considering the multi-particle at this minimum two particle, or if you have the more transition from one state to another state, or if more electron, you have a multi-particle state. So what Dirac trying to take this opportunity to, instead of going from multi-particle, Dirac tried to interpret this negative energy in another way around. So when Dirac tried to make the rule, or the not Dirac, sorry, the Feynman tried to make this Feynman rule in his own approach. The Feynman approach actually worked both for Kerr equation and Dirac equation,
Okay. Interesting.
because what the Feynman rules was needed.
Okay.
he does not introduce his vacuum state, then the possibility of this Pauli's question principle was not there, which was there in this Dirac equation. This is one of the things. And also he considered what are the particle that is not create the hole itself. He just considered, okay, we can define this absence of electron. Instead of calling it a hole, we can consider this negative energy.
Mm.
The corresponding which have a like negative energy and negative charge. And
Mm.
opposite to the negative. If I consider electron, what are the antiparticle? The dynamic. If I try to understand dynamics of antiparticle, we just need to change the energy and change the charge.
Mm.
So from the Feynman approach, if you try to understand dynamics, a negative energy particle propagating in backward in time, but in Feynman and for antiparticle, positive energy antiparticle that is propagating forward in time. So basically, what he did, he tried to define the same. He tried to solve the same problem in other way around. He said, "Okay, I don't need vacuum state,
Mm.
so I can deal with both Green-Gordon equation and Dirac equation. That means I can deal both bosonic particle and fermionic particle.
Mm.
And instead of considering a new concept of new particle, whatever we call like hole, we can define the antiparticle based on the energy and momentum.
Okay.
And if momentum is positive, if I consider it is forward in direction, if momentum is opposite, to be negative direction.
Yeah.
And as we are in this energy momentum and four-dimensional space, so what he said, okay, we don't need to think in terms of energy and momentum separately. Even we can think just four momentum.
Mhm.
So if I consider a particle, if the particle for momentum is p mu, but the antiparticle is minus p mu. So the problem will be more easy to solve.
Yeah.
That was the main Dirac was not Dirac, the Feynman, what he was trying to do.
But we never in the so we are able to observe antiprotons or anti-electrons or antimatter, anti-electrons, specifically positrons, but we are never able to observe a negative energy particle, right? Which is going backwards in time. So the way I see it is like, say, for example, if you observe a particle just before the collision happens, then that is like an indication of a particle that goes back in time.
Uh, exactly, yeah, exactly. This is the kind of the diagram I'm showing right now. It is exactly just to show, just complete that what you're talking about. So, probably this one or later or this one probably. Yeah, or probably this one with the better one. Probably fine. This is just a kind of simplified version of the Feynman diagram. So whatever we are considering the particle, whichever let's consider this is a negative energy, positive energy particle, pi plus, is make a scattering with. Let's first explain this one, then I'll come to your point what you said. So in this diagram, I'm basically showing a absorption of a particle, and it suppose that consider there is a state kind of, let's consider vacuum state. One particle come to the vacuum state, it is absorbed, and then again is re-emit the particle. There are many physical phenomena like this. So let's consider one example. There is some potential here. I define with V. So the time is going along this direction. The positive time is going in this direction. So one pi plus is coming and absorbed by this potential V. And at the same time, now here I can say it can absorb pi plus, and from this diagram also it can absorb a pi minus.
Okay.
So I can say it absorbs a pi minus, and also the same thing I can say after that it. So after certain time, I can start from here. If I just doing in terms of classical non-relativistic domain, I can start from here. But instead of that, I change the time frame, just going backward in time, and then said, so this potential, whatever this V potential, first is absorb pi plus and pi minus. So that's going along the time. So it absorbs this pi plus and pi minus, and then it create a pi plus and pi minus pair at time t1, and then is emit the pi plus particle. So what is important here?
Is this a real world scenario?
Yeah, there are many. Suppose that concept there is one kind of some of the potential is like let's consider is a kind of scattering system. Like when talking about this Compton scattering, let's consider Compton scattering. So, though in Compton scattering it is not something absorption happen, but it's something like scattering happen. Let me give you some another example.
What is V over here?
This is a potential. I'm just showing this potential is something which absorb. It's so much high energy it can absorb. Yeah, okay. Let's consider how this virtual photons are created or generated. Let's consider you have some vacuum state. From the back, so when you have two electrons, so you have some. Let's not exactly the same scenario, but one electron and one positron
Mhm.
in quantum dynamics. Then when you try to interpret this interaction, so where she said this was emit some photon. So no, this will not be a good example. And let's put this one. What I was trying to think some proper example which can give some physical. I need to think. Uh, is there any possible interaction like this? I need to think any example of this one. Okay. But the story what I was trying to tell,
Mhm.
if I go back to the previous state, let's try to see some like real classical scenario. Okay, I
Mhm.
mean the non-relativistic case. So
Mhm.
one pi plus it is absorbed by this potential,
Mhm.
and then it is emit. Okay, I can give you an example like this. Let's consider uh, one one photon is
Mhm.
it fall into some electron. Like suppose there are some let's consider this is a nucleus, and there are some electron in different state. And when one photon is incident on this state, on this atom or nuclei, then whatever, let's try to draw this one. So when the photon will be incident on one of the electron, it gets some energy
Mhm.
and it goes to the upper state. And then after certain time, so there is a vacancy created on this. There is make a hole in this because absence of electron. After a
Mhm.
certain time, this whatever the electron is jump from this state to this state, they will fall
Mhm.
back once again to the lower state because with some time it will emit some energy.
Mhm.
I mean, when one photon is fall into one electron, so because of this electron, it gets some energy. So it absorb this photon. So this get electron get energized. So it go from lower state to upper state, but that is not a stable state. So it need to come back to a stable state at some point. So when it fall back to stable state, it again emits some energy because that's how the Bohr postulate happened. So when any electron fall to the one state to another state, it emits some energy.
Yeah.
So I think this is one of the example could be like the previous one what I'm talking about.
So the
Just
way I'm seeing it is like just I'm imagining. So we are always seeing like the electrons getting created out of vacuum, out of nothing, right?
mhm,
There's no perturbation. Suddenly electrons can come from a field. I know we are not talking about a field, but just hear me out.
mhm,
Uh, so we are like seeing scenarios where things happen out of random, suddenly, and then it disintegrates to something else. For example, like we saw like electrons suddenly forming, and then later on it disappears into like into a photon, right?
Mm-hmm.
So the thing that is happening randomly, right? I don't think it is happening randomly. Something is going to happen in the future, and that thing has happened in the future, and we are observing in the past, as
Mm-hmm.
traveling back in time.
Mm-hmm.
So we can interpret everything like even there were example that a relativistic example, non-relativistic example that he gave, where the electron moves from like one lower level to upper level. Again, it comes from upper level to lower level.
Mm-hmm.
So why should it come from upper level to lower level? What do you mean by instability? So the way I'm thinking is like why we call it instability is because so it is like we are thinking that it is coming from upper level to lower level. No, it is basically is backward in time. It is going from lower level to upper level. But if you are thinking the reverse of time, it's we are seeing it as like upper level to lower level.
Mm-hmm.
So that is where I'm seeing like these negative energies and traveling back in time.
Mm-hmm. Yeah, I mean, yeah, I mean, it's a good way to think also. But when you talk about the stability one, I mean, if I just try to understand physically instead of
Huh?
imagining on this, like that is how the Bohr postulate was defined, right? I mean, electron could not be the particle could not be accommodated in any state. The particle for every state there should be some particle which have some integer number of angular momentum of the given state. That's how the Bohr
Correct, correct.
postulate was defined, right? I mean, any electron cannot accommodate in any state. It's supposed to have this particular state of, it will be accommodated in particular state corresponding to its angular momentum conservation.
Correct, correct. But the
So
thing is like, why should it come back from higher level to lower level?
okay, so the reason again the reason is that so first of all, why the electron jump from lower level to upper level? Because of the incident photon.
Correct.
So
Well,
because of the
higher level
incident
to lower level.
photon, the electron gains some energy, is energized, is excited, and then because of that, so this energy state was not accommodated because that is not energetically favorable for that electron, that particular state. So it needs some energetically favorable state. So it's jumped to lower level to upper level because of the energy favorable energy state, and then the electron will be supposed to on that state. If it will be remain on that state, if that state is energetically and in terms of angular momentum, it will be favorable for that. If it is that, it will remain on that, it will not fall back. But if that state where it jumped, if that state is not energetically favorable for this electron, or is in a, or this angular momentum is not it doesn't disturb or perturb the whole system. I mean, this electron is jammed because it get energy. But if it is do like that, the whole atom will be disturbed or perturbed. But what nature wants stability or equilibrium. So that's because the entropy should be going going to maximize, so the system, so or it will not maximize, what is the word is called, uh, indivisible least, so that the system will be in equilibrium. So if the electron which is jump from lower state to upper state, if it does not make the whole atom in non-equilibrium, it could be remain on that state. But if it disturb the whole state, if it is part of the whole state,
Okay,
then it will be forced to come back to the original state, because of that the whole system was in equilibrium.
okay, okay, okay.
I mean, this is just to keep in mind this Bohr postulate, because that's how Bohr was able to explain why the atom is stable, or this is the atomic stability. I mean, there is no, I mean, why electron could be in particular ones, it could jump anywhere, right? I mean, but it's not possible because the stability of the atom. That's the nature. Nature wants to make thing uh, stable, so that so the entropy will be go what we expect it. Otherwise, the system will collapse at some point.
Okay.
Okay, so we'll take 5 minute break,
Okay.
then we'll come back.
Okay.
So till what time you have time?
I have another 1 hour.
Okay,
Like
fine. Oh, great.
yes.
So I think let me see how this slide I have for this negative energy. Okay, I have 10 slide, and then we'll just introduce at least this Dirac covariance stuff. And
Okay.
okay, so I'll be back in 5 minutes.
Okay. Okay. Thank
So just to the point you just said, like the negative energy you are thinking about, it will be. I mean, now in this picture I'm showing right now, this is like a non-relativistic non-relativistic picture where the possibility of negative energy obviously not there in non-relativistic dynamics. But when we are in the relativistic domain, relativistic quantum mechanical domain, then the possibility of negative energy, what we get from that Dirac equation. Then what Feynman tried to interpret this negative energy source, he said, okay, in this relativist non-relativistic domain, that consider this pi plus, it is scattered by this potential, or let's consider when this pi plus is fall into that one, probably it happened this particle, its energy changed from positive energy to negative energy, though it is
you.
not possible in non-relativistic domain. But in relativistic domain, if this happened, so what Feynman interpret, he said, okay, in 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 quantum mechanical domain, if there is a possibility that this pi plus, which is going forward in time, which have a positive energy, and because of this potential, if this particle energy is from positive energy to negative energy, where the particle is moving in the forward in time when it is positive energy, now if it is positive energy, it can go like this way along with time. But
Yeah.
if it is negative energy, then this pi plus, let's forget for a moment this pi minus, the pi plus, which is negative energy, it will go backward in time,
Yeah.
and that we can represent by pi minus, which is antiparticle. And then again, suppose again this particle is get energized by another potential, then its energy change from negative energy to positive energy, so that particle can go forward in time.
Okay.
Is
Okay.
it,
Okay.
this is a picture of what is interpret. So in non-relativistic domain, we don't have a possibility of negative energy. But in relativistic domain, if there is a possibility to create some negative energy particle, that negative energy particle can go backward in time instead of going forward in time. So this backward in time is represent particle which is having negative energy.
Mm.
And then I think this picture also kind of similar picture. Whatever the potential is there, this potential had enough energy, so it can absorb the particle like pi plus and pi minus. So just to represent that, I can say this potential absorb the pi plus and pi minus. So for pi plus, which is positive energy, for the propagation of that, I use the it is propagating forward in time, and pi minus, which represents your negative energy, it's supposed to go in that way, but I just represent backward in time.
Okay.
Okay, so what is the main story or the main message from this story is that whenever you consider the negative energy solution of a wave function, which basically represent a specific state, that also be similar to positive energy antiparticle. So negative energy particle, that is positive energy antiparticle. So that actually help us to going from multi-particle to single particle. That means what I am dealing here, I am just changing their energy and charge. So I don't need to deal with multi-particle. I can just simply deal with single particle, just different energy and different charge. So that's
Yeah.
actually because that is one of the when we discuss later about the more into quantum field theory dynamics, we can understand how difficult it will be when you try to deal with multi-particle. So to
Mm.
make the story simple, Feynman said, okay, this is a kind of a simple picture, which that's why Feynman diagram is so famous because it's make the story more simpler. Because if you have only one particle, to understand dynamics of one particle is more easy than dynamics of two particles. If you have two particles, they have interaction, there's more complication will be there in the dynamics. Okay, this is same thing I'm talking about. Now this is something new what I'm going to talk about. This is about how we can this thing also we discuss later about interaction. Sorry, no, this one. Yeah. So, like whenever later we talk about the coupling or something, then we need to know about the probability current density. So here I'm talking about probability current density because this is a four vector, and this four vector has both the density, which is basically a scalar component, and the vector component. Now, if I want to define the for the pi plus whatever the interaction or the probability current density, later when we do the mathematical calculation, I will show you that this is nothing but the charge times the probability current density for positive charge. If I consider pi plus, for pi plus positive charge, I need to know the charge of the particle plus probability, sorry, not plus, charge of particle times the
Okay.
probability current density for the positive charge solution. Whatever the solution it will be at this point, I'm just considering the positive charge solution. And this is, if you just I remind you, I already discussed, this is my probability density. If you remember, it's like 2 n square. I can write it. 2 modulus of n square times energy. So whatever the probability current density, this probability current density for pions or pi plus, it will be charge times this rho. So if I know what is the momentum of the particles and the energy of the momentum of the particles and energy, or basically I can write down the probability current density. So this is for the pi plus. That's why this Feynman diagram is so easy. You can, I mean, you don't need to redo the calculation once again to get this probability current density for pi plus. If you know for pi plus, you can also get it for pi minus. Just what you need to do, you need to just change the charge. And I guess just I can, so if I just charge from, like, this is the definition I can get. Sorry. So for pi plus it will be E plus, for pi minus it will be E minus.
Yes.
And if I just incorporate this, so if I just want to convert this pi minus E minus to E plus, so I have one minus sign, I can just take it inside this one. So this is a positive for momentum, and this would be negative for momentum.
Yeah.
So what is the important thing? I mean, if you know the probability current density for the particle, which is at the moment for momentum, let's consider p mu for the particle, and for antiparticle it will be p minus p mu. So, and this is something very easy to calculate or easy to know what is the for momentum, because it is just energy and momentum relations.
Yeah.
The second thing is, I just extend this discussion more because just to give you the full picture of the story, there is another process that considered the process of emission process. So this is the again the Feynman diagram, simplest Feynman diagram with respect to time. A system, it can emit some pi minus. If it is a kind of like unstable particle, it can emit a pi minus with positively charged. Then you can just change. So when it, let's try to understand, when this system, when this potential or this system emit one pi minus, then the energy of this system will be changed because it's emit one particle. This particle takes some positive energy. So the energy of the system will be decreased by E amount, the energy E amount, and the charge also, because this pi minus takes some charge or negative electron, negative charge, because it is negative particle. And that is equivalent that the system will get absorb some charge. So instead of getting negative charge, which is happened because of the emission process, if I just think in other around, that the system is get absorb some positive charge and get some energy. These two are identical, right? I mean, you emit some negative energy, so emit some pi minus, which have a negative positive energy, which is same as absorb some pi plus with negative energy. This is just a kind of identical scenario. So this is what I'm going to say. So if I consider this system which emit one pi minus with positive energy, this is identical. It absorbs some particle which having charge pi plus and negative energy.
So emit a pi minus with a positive energy. Emit a pi minus with, and this minus sign over here, does it represent just the particle type, right? It's a pi
Yeah,
minus.
this is just negative charge particle. This is positive
Negative
charge
charge
particle.
particle. Yeah.
This is
First charge
negative.
particle.
The negative. This is a negatively charged pion, who is having positive energy, which emit by the system, that is equivalent to absorb a positively charged particle having negative energy.
Yeah. So which means like the energy of A is going to reduce in both the cases.
Yes, exactly. It is reduced voltages, but once in case of positive, we just label it as a positive energy. In other case, we label it as a negative energy. But ultimately, it's lose the energy, right?
Yeah.
I mean, this is just a kind of two possible interpretation, but the picture is same.
Correct, correct, correct. So like so have you seen in this scenario like a negative energy being absorbed and the total energy of the system going down? Have you seen this scenario in real
Just a
life?
second. Can you repeat, please, once again?
Have you seen this scenario in the real life where a negative energy particle is being absorbed, and the total energy is going down?
No, that is not. I mean, that's. I mean, then it will depend on the what system you are considering. Suppose that consider your system already in the excited state.
Mhm.
Then it could possible. But if it is in the normal state or the ground state, then it's not possible, because if the ground state is zero, the ground state represents zero, then
Cannot
it's not
go
possible.
down.
But if the suppose system already in the excited state, then
Yeah,
it
we
is
can assume excited state. We can assume excited state. So
Mhm.
we have seen like in that scenario. Yeah, yeah, this is a good point. So if it is excited state, it absorbs a negative energy particle
Then it can go to the down
and comes to the lower state.
lower state, so get the equilibrium. I mean, ultimately the system always trying to get equilibrium. If your system allow you, I mean, the system allow you to do whatever you want to get the equilibrium.
Hmm.
That means if the particle is already in excited state, then the whole system will allow you, because the system itself want the equilibrium. So that means that in that case it's possible. But otherwise, if it's already in the ground state, then it's not possible.
But we always see, I mean, we don't observe this, right? That the second scenario where even in a excited state, we don't observe, we don't observe that when there is like when the system is in the excited state, something happens and the system comes to equilibrium without releasing a photon. We never observe this kind of scenario, right? Always when there is excited state comes to like a normal state,
Now,
equilibrium state.
if you consider photon, then for photon is, because photon is a neutral particle, right? And neutral particle in the sense, for photon is not possible, but it can emit some, it can absorb some other particle, which is a charged particle. Then it's possible, right? Because if you consider photon is a photon.
Yeah, no, what I'm saying is like we are excited state to an equilibrium state is always followed by a release of something. That is true, right? I mean, like we never seen like suddenly it became from like a excited state to normal state
No,
without
then it is
anything.
possible. There are many examples of such. I
Okay,
mean,
okay.
I can show some of the picture defined spectroscopy. It is possible if the system is in the excited state. It could possible.
So system excited state
Physically, it's
comes to
possible.
normal state without emitting anything.
I mean, it could absorb something, right? Instead of emitting, it could
Yeah,
absorb
that's
something.
fine. Observe, that is what I'm trying to find.
Yeah.
Like the right hand side picture, right? A absorbs negative energy. That is what I'm trying to see. Like when the
Mhm.
real life, are you able to see these things? Like system gets from excited state to normal state without emitting anything.
Yeah, I mean, yeah, that is not possible because otherwise, I mean, if we think in terms of energy, because it's want to get some kind of favorable state to lower state, then it need to release some.
Exactly,
Yeah,
exactly,
yeah,
exactly.
but
So that is
it
where the
could
right hand
absorb
side
something.
diagram, I'm not able to see like in what scenario that we have seen that a higher like excited state to equilibrium state without emitting anything. So
Mhm.
it's like without emitting anything, I understand the energy should be conserved. So either it should not, like what I'm saying is like it should not emit anything means it is absorbing something, absorbing a
Yes,
negative.
exactly. So if you talk about in terms of absorption, then it's allowed. I mean, it could absorb something so that it can get to the favorable state. But yeah, I mean that's again, if you only talk about the absorption of yeah, I mean it's completely depend upon the state. I mean, if the state is preferable to absorb, if it absorbs some negative energy.
But have you seen that? Like, have you seen that scenario?
I need to check some article. Probably I need to check
Yeah.
some article.
Yeah.
But conceptually it is
Probably like
possible.
if you're able to find that, right, then we'll get Nobel Prize.
I don't I need to check some article I guess. But theoretical is possible if it is higher state, it can absorb some negative energy. So like plus 5 minus 2, so it will be 3, so it can go down to the lower energies.
Yeah,
Theoretical,
yeah.
but I need to check it's experimentally possible or not.
Exactly, exactly. That's exactly
Mhm.
my point. Experimentally, have you seen that? If you're not seeing that, then probably like there's a Nobel Prize waiting if you're able to find it.
Probably there are some, probably already someone got the Nobel Prize for probably. I'll check it is possible or not.
Okay.
Okay, so the one more thing just to computer study, just I already told this one that so in case of if you can just think the same thing also in terms of form momentum, like I mathematically I saw I think one of the slides here, not this one. Yeah, so if I just wanted to change the particle type from pi plus to pi minus, then the thing whatever we are interested, we if something is from this is nothing but a form momentum. So if you go to the antiparticle, just your form momentum will be a plus to minus. So this is I think one of the biggest achievement from Feynman approach that if you know about the form momentum of the particle, then you can just replace for antiparticle with and minus of p mu.
Yeah, that
And
that is
also,
interesting.
yeah,
I've seen like in the quantum field theory, like each particle is represented by field. So with this interpretation, we don't have to have like a field for electron, a separate field for positron.
yeah. So you can
We
just
can represent
simply
it.
play with the corresponding form momentum with that.
Exactly.
And also it's another advantage of this Feynman approach that it's also valid both for bosonic particle and Kerguelen and the fermion. I mean, it's somehow at some point merged both Feynman for Dirac equation and Kerguelen equation because Dirac
Okay. Dirac
when
does not
Dirac tried
support
to
the concept.
reinterpret for bosonic particles, he failed from his way of from his approach.
Yeah.
Okay, so I had few homeworks which it's very simple one, but if you find some time to play with,
Mm.
it's just very simple one. Like in one of the homework, I gave the wave function. I said this is the free particle wave solutions, and then you need to show me the
Okay, okay, okay.
probability current density and which is proportional to just if you just take that definition we already discussed few times the probability current rho and j, if you just take this one do some derivative with respect to time with respect to space, you find out that this probability current density, probability, now I'm talking current, I mean probability current, this J mu, it is always proportional to the P mu. We will use this one also later when we're trying to do some scattering, when we try to understand what is the coupling strength, that time we always use this J mu. It will very often come to our picture. So
Yeah,
I give the
coefficient of
definition
both
of
sides, right?
rho
Yeah.
and j here. You just
Mm.
simply need to take the phi to like, for rho you need to do like time derivative, and
Mm.
phi j you need to do the space derivative.
Okay.
And the second thing also, this is also very often now used. One thing is about the whatever the sigma matrix or Pauli sigma matrix we're talking about. They follow the commutation relation sigma I and j, and also they had anti-commutation relation. So you just simply need to take that matrix representation of sigma and j. Just you can just take component by component multiplication. You can find out this will be equals to 2 times sigma 3. If you take sigma 1 and sigma 2, you find it with 2 times sigma 3. And whatever the epsilon I mentioned here is called Levi-Civita constant, epsilon ijk. If ijk, if the even permutation, it will be 1, odd permutation equals to -1. And if any one of the two index are same, or three of them, or any one of them are same, then it will be 0.
Okay.
That means if you take the combination like 1 1, then it will always 0, because this
Zero. Yeah.
this Lebesgue constant make it 0. And also you can see what is the anti-commutative relation between them.
Okay.
And third one is, today I think when we talk about the Dirac equation, once we use this mathematical identity, so you can just take sigma dot p, and if you just square it, that means you just need to do the matrix multiplication. I mean, it is easy, less multiplication one by one. You can find out it is momentum magnitude times identity matrix. This
Mm.
is actually used in when you try to derive the Dirac equation.
Okay.
And then another homework is, again, I consider the free particle solution for the equation psi, that is this spinner part, 4 by 4 spinner but this is a bipe spinner with this plane wave solution. Then what you need to do, this is just like a derivation for this equation, like e minus m times phi. Just you just need to derive this two relation, which is I think already we did in terms of gamma. But if you are interested in terms of alpha, you can do this simple mathematical one. And then this is the one point what I wanted to talk about. What last time we talked in terms of gamma matrix, but today we discuss in terms of alpha and beta. But there is a relation between them, and that is like, what is a gamma 0? That is nothing but the beta what we use today, and other gamma, which is alpha. If I take gamma I, this will be beta times alpha I. So you can just simply take a definition of gamma, and you had beta and alpha. You can just make a comparison, and you can see this relation is always
Yeah.
true.
Yeah.
So this is the way, I mean, if you just take from the last class, and if you want to convert from last class to this class all derivation, if you just simply use this notation, you can change between them. Because in some of the book, like sometimes they use alpha beta gamma, this alpha beta. Some of the book they use gamma notation.
Okay.
And this is another one. So sometimes when it consider this Dirac spinner, we also define something called conjugate spinner. So
Mm.
to do the, sometimes instead of taking only psi, we use psi bar, which is called conjugate spinner, which is nothing but psi dagger gamma 0. So this
Okay.
this spinner we call it like a Dirac conjugate spinner. And knowing that this is a definition, actually this is just way it's defined. Then again you need to take the definition of probability current, the
Mm.
definition we already have, and then you need to check this is true.
Okay.
Okay, so this is about the first part of the video. So in the first part of the lecture, where we talk about the negative energy, we try to understand the different interpretation, one from Dirac, one from Feynman, and then the final interpretation of negative energy will be more convenient from the Feynman, because I like that approach because it's make the picture more simpler one compared to the way of Dirac because of the multi-particle.
Having some practice will be really good actually.
Yeah, I mean
And
sometimes like yeah, when you do, I mean even like when I mean nowadays when you are doing like in doing the PhD, there was very small time when you were doing some math because mostly writing the code to do data analysis. But yeah, but when for this theoretical understanding until unless I do something by myself on pen and paper is very it's the picture is not clear at least. But when I do this mathematical derivation at least once for the lifetime, then it become like more I can just always remember I did this one. So it's back
exactly,
on the mind.
exactly, exactly.
Okay, great. So
Perfect. So,
next we meet
what are you
on
doing? Any plans for rest of the evening for you?
rest of the
Evening? Any plans for after rest of the evening?
we had some friends will gather together because yesterday we had like usually on Friday on Sunday I am from
Done.
Kolkata, so like Bengali. So I mean in our institute there are more than 10 Bengalis are there.
Oh, wow.
So
Wow.
usually on Sunday weekend we meet together. Everyone sometimes we cook together or we just bring some Bengali food and
That's
as I
amazing.
like to cook, so it's like I used to cook biryani almost
Oh,
twice in month on weekend.
yeah, that is amazing. Like, I mean, when I was in France, like 2000s, like 25 years ago,
Hmm.
I mean, finding Indians was very difficult.
Hmm.
Forget about, like, I'm from Tamil Nadu,
Hmm.
but actually I speak Saurashtra, so I'm a good, like 1000 years ago, I was a Gujarati. So
Hmm.
I came to Tamil Nadu like after this Muhammad Ghori and all those fights, wars and everything. So we are entire thing migrated 800 years ago. So in house we speak Saurashtra. But we are in Tamil Nadu, so like we speak Tamil. So in France, like we couldn't see even Indian, any Indian at all. Like we were in south of France,
Hmm. Yeah,
Nice,
okay.
yeah, Nice area. So we couldn't see any Indian. Like finding one Indian will be like extremely happy.
Yeah, yeah. I mean, yes, that's true. And
And
like
if you have Bengali friends,
whenever
will be
we had friends, I mean here we had like so many Indians. I mean it's more in the institute also there's many Indians. I think
okay.
nowadays the whole Europe is run by Indian mostly. I mean if you go to any research institute or any places, uh,
Yeah, I can see that. Like one funny story was like back in 2003, I went to Grenoble. So the first thing like that's the first time I'm going to that city. It's famous for like institution and ST Microelectronics and Texas Instruments. So I went over there. The first thing I saw was a Chinese restaurant. I was wondering like how come Chinese are over here? There's no Indians. Then I turned my head on the left side. There is Indian restaurant also. So where are you going? Everything.
yeah. I think in Warsaw also it is full of Indian restaurant. I mean there's few of them are good, but I don't like any of them because I feel I cook better than them. But
Yeah,
yeah.
it's meant for the European style. Like I
Yeah,
also
yeah. I mean,
like they
even
have
when they
banned
call
all
this
these
Indian
spices and
restaurant, I mean, I always feel the word often because when they call Indian restaurant, they had mostly like food like from uh not India, like Delhi food or like there are some food from I mean in Bengal we had so many cuisines. In I mean like in time I like this South Indian food also.
yeah,
But some most of them they call this Indian just to grab the crowd.
I agree with you. Agree. Okay.
Okay, great.
Have a nice
So
evening.
yeah,
We'll see
so
you on
we'll meet on Wednesday.
Wednesday. Yeah.
Okay,
Thank you,
okay.
Haratan.
Bye
Bye.
bye.